the weights will swing during every... What the hell's going on? Be quiet. I'm trying to record. Welcome everyone. Today we're going to be finishing up the recurrent neural network that we've been building from scratch. Two things we need to do. We need to add the step decay, momentum decay to the network. Another thing we also need to do is we need to go back and we need to fix our dropout. So we've implemented dropout incorrectly. We just need to go and fix it up. The reason why we implemented it incorrectly is if we go into the forward pass, actually let me pull up where I've drawn it here. Where's my pen? Dropout is essentially just randomly turning off the nodes. And the reason why you want to do this is because you want to prevent the neural network from just keeping or just memorizing information in these nodes. When you turn off nodes, they now have a value of 0. And so the output when you implement dropout is a lot weaker than it normally would be. So then to compensate for that, you have to divide it by the probability of being active. So rather than it outputting 7, once we divide it by our probability of being active, we're now outputting 14, which makes up for the fact that this node is now turned off. The problem is, what the heck did I just do? The problem is when you do that, the dropout itself, so turning off this node, and then this division here, both of them are affecting the output. And so when you're doing your backprop, you have to keep that in mind, meaning that for every layer, you have to incorporate all this dropout stuff that you've done into the backprop section. What we've done here though is for each time step in the output layer, we are implementing dropout. However, this self.dropout mask variable, it will only keep the last dropout mask in memory, and it will just completely get rid of all the other dropout masks that we've created. So for every time step, we want to keep the dropout mask that we applied and then incorporate that into our backprop. I'm gonna change this into dropout masks, and we're gonna have it as a table. And so this table, for every forward pass that we do and every dropout mask that we generate here, we just want to go ahead and we just want to add it to our dropout mask array. So then when we're doing backprop, we just want to incorporate those different masks that we've generated and we've used to manipulate the outputs from each time step. We just want to make sure that we incorporate that into our backprop. I think that's it. Let's try it out. See what happens. See what breaks. What happens? What breaks? Huh. Looks like it works. So it works. We didn't run into an error. It's a good sign. And I think, logically what we've done makes sense, right? Annealing basically says, okay, why don't we start off with a high learning rate towards the very beginning? Why don't we start reducing that learning rate as time goes on and as we learn more and more, yada, 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 so that towards the very end, once we're almost at the minimum, you're only changing the weights very, very little. So at the beginning, let's quickly try to make our way down that gradient, reduce the error. But then towards the very end, let's start fine-tuning the network a little bit. I guess for the learning rate, there are two types of annealing functions. I don't know why maybe there isn't for me, or maybe I just didn't implement it. So the first type of annealing is called just halving. And essentially what it is every 2 epochs, what you're going to do is you're just going to take the learning rate and you're just going to divide it by 2. So over here, we're just going to take our new learning rate will just be equal to our old learning rate. So 0.1 and divide that by 2, and then we get 0.05. The fourth time step, again, do the same thing. That's how that works. So is there a name for the second one? Oh, I think it's called step decay. So this one's actually pretty simple. Say our interval is 2 epoch, and we have an initial learning rate of, 0.1. Every x steps, or every x intervals, we're going to decay our learning rate by, let's say for example here, we're going to do it by, actually, you know what? Let's start with a learning rate of 1, just make it simple. And then every number of steps or every interval, we're going to decay by 0.1. At interval 1, we're going to have a learning rate of 1. At interval 2, we want to decay that learning rate by 0.1. And so our learning rate just comes down to 0.9. And so then at interval 4, same thing. So every interval or every predetermined step that you've entered, all you're going to be doing is you're just going to be subtracting the decay from the learning rate. If I want to use the step decay rather than halving that this defaults to, how do I pass that through? So what I could do is I could do this. I could initialize it as a table. You know what? No, that's too convoluted. Simpler option here is to just separate these out into 2 different functions. I don't know why I tried to group them into 1. That actually doesn't solve anything. What I'm struggling with is when you're initializing the network, if you specify that you want to use step decay, I'm just going to stick with step decay. So if you specify that that's what you want to use, the one thing that I have not implemented down here in my train function is the ability to pass arguments to that step decay function. So either pass whether or not you want to use halving or whether or not you want to use just regular step decay, whether or not what the constant is or even what the intervals are. None of that is implemented. I didn't want this to be a table. I wanted to avoid using a table or a dictionary for it. So I said, okay, you know what, why don't I split out this this function here into two separate functions. So one function specifically for halving, one function specifically for step decay. You also need to pass in the interval for both of them. Then you need to pass in the constant for the decay one. So I need to figure out how to do that. Well, I could leave it as a library. Sorry, as a dictionary. I could just do is type is equal to rnn dot step decay, and then I can just pass in my interval and constant. Come down here. I'm going to pretty much implement the exact same thing here. So I think we're good to test it out. I made a mistake. Okay, I think I'm just missing my comma there, missing a comma. Let's try this again. We start with a learning rate. Why is my momentum like oscillating? Here are two problems. One, learning rate is staying the same. It's just staying at 0.001. And my momentum, it looks like it's kind of like, it's just seesawing, right? Going up and down, up and down, up and down. And I don't know why. So let me go ahead and let me just print that out. Let me go ahead and let me just print that out. What I want to see is whether or not learning rate or mu gets changed. So my learning rate is pretty much 0. My mu is 0.99. Why is it not showing up in the graph? And why does my learning rate go from 0.01 to just 0? Okay, what have we done? Let's take a step back. Oh, okay, yeah, I know why. Because our decay is larger than our actual learning rate. Let's do that. Okay, so what we can see is, and there's no good way for me to like pause this, so I'm just gonna break it. Our learning rate starts at 0.001, and as time goes on, every single time we hit the interval that we set, we then go ahead and we subtract whatever constant that I determined. We go ahead and we subtract that from the learning rate. As time goes on, the learning rate gets smaller and smaller, meaning that we update the weights. The updates that we make to the weights get smaller and smaller over time. Again, allowing the network to fine tune itself. And so at the very beginning, we start off with large adjustments, but then towards the end, we start making smaller and smaller and smaller adjustments just so we can minimize the error as much as we possibly can. And then similar thing happens for the mu as well. Oh, an hour, 16 minutes in. This was supposed to be 20 minutes, 20, 30 minute stream.